Good morning, everybody, and welcome to our last webinar for the year. And this particular webinar deals with solar panel testing, more specifically, some of the electrical safety tests called out for in the solar panel standards. Now, we have a lot of material to get through today, but before we do so, I have a couple notes on just WebEx in general. If you do have questions, you're going to have two utilities at your disposal. And you're going to notice them on the right-hand side of the screen. You have a chat and a Q&A utility, and they are a little different. If you have questions about the material that I am presenting, please use the Q&A utility. We have our applications engineer, Syed Abidi, helping out today. He's very knowledgeable with this stuff, so if you have a question, throw it out there and he'll be able to help you out. Any questions related to the running of the meeting, so if you're having problems with the audio or the video or something along those lines, use the chat utility, address that to Jim Kennedy, and he'll be able to help you out. He is our host. This webinar is being recorded and will be available in a few days to view on our webinar archive, and I will give you the link to that website at the end of the webinar. If you would like a copy of the slides in this presentation, just let Jim know, and that's jimk@asresearch.com, and he will be able to send those over to you. So that being said, let's get into the material. Like I said, we have quite a bit of material to cover today. I expect this webinar to take anywhere in the neighborhood from 45 to 50 minutes, and I always like to leave a few minutes open at the end in case there were any questions that perhaps Syed wasn't able to get to. Now, there are those questions that tend to be rather in-depth, and we really just don't have the time to discuss them here. If that is the case, we will be giving you an email at the end of the webinar that you can send us your question, and we will be more than happy to discuss in more detail, and you can always feel free to call myself or Syed to discuss on that further. So what we're going to talk about here today, like I said, is in line with the electrical safety tests that are called out for in the solar panel standard. And we're not dealing with every electrical safety test here that just would not fit into an hour webinar. Specifically, we're really going to be talking about your ground bonding, your ground continuity, your dielectric withstand test, and your insulation resistance test. So to talk about them in the standards, we first have to understand the concept of these tests. So that's the first thing I'm going to cover. I'm going to talk about bonding versus continuity, the dielectric withstand test, also called the Hipot test, the insulation resistance test, and then we're going to get more into the solar testing standards, how the standards relate, what each standard says, and then finally we're going to get into the wet insulation resistance test. Now, the reason that I am saving that for the standards part of it is because this is kind of a unique test per the standards, so I think it's important to get where the standards are coming from before we really start talking about this test. And then we'll go over a couple testing method examples and call it a day. So first things first. I like to always start things off when we're talking about continuity and bonding by defining terms, because standards and people and the various applications I've run into, they really define continuity and bonding differently. One person might mean continuity one way, whereas we mean it another. So let's clarify a couple points on that. When I say ground continuity testing, this is just a test that's used to determine if the ground or earth wire of the product is intact. That's it. We're not talking about heavy loading of the circuit. It's just a small voltage applied to the earth pin of a product on their ground pin, and then the other side of that would go to the chassis, and we just want to know if current flows, just a small DC current, and what that would tell us is if there's a path there. Something as simple as an ohm meter, resistance measurement, or a battery buzzer combination, or if you've ever seen those little pens where you attach a little clip to the chassis or the ground pin, and then you take the pen and you contact the chassis point and you have a little light bulb on top, and if that light bulb lights up, you have continuity. So when I say ground continuity, that's what I'm talking about. Ground bond, I'm talking about actually loading down the circuit. And I know in the solar standard, what they call ground continuity is what we call ground bond. So just to clarify, anytime you're dealing with a higher current, anything over like ½ amp, I would consider to be a bonding test. So this is a test that's used to verify the current carrying capacity of a product's ground connection. A continuity test isn't going to do that for you. All a continuity test is going to tell you there's a path, but how much current can that path handle before it finally breaks down? So what we're going to do for a bonding test is high current is going to flow from the earth pin of a product's line cord, or it might just be a wire, through to the chassis in order to determine if the cabling is capable of handling this excess current flow. And what we're looking for here is, hey, if we have breakers in the circuit, will these breakers trip if something goes wrong? Can it handle this fault current? So it's basically looking at the integrity of that earth path. So the earth bond test or ground bond test actually checks the safety ground circuit of the DUT to make sure it can adequately handle this fault current if the DUT insulation should fail. Because as a consumer and using an electronic product, we really have two main lines of defense here. We have the product insulation, and we have the ground circuit. And if the insulation fails, you better hope you have a solid grounding circuit, because otherwise you might be in trouble. So basically what's happening here is we have high current flowing out through the ground conductor to our solar cell, and it's basically looking for a chassis point, which let's just say this is a frame chassis point. It finds it and goes back to the return, and if it can handle that 25 or 30 amps or whatever the case might be, we know we have a good ground connection. That's an earth bonding test. So what's going on here? Well, this is kind of the circuit diagram. So on the left-hand side, this is basically our ground bond tester, and on the right-hand side, this is our solar panel. So what we have here is, here's a pass condition. So you can see current flowing from the ground wire, and it doesn't necessarily need to be a three-prong plug. It could just be a straight wire, but just for the purposes of this demonstration or this example, I'm just going to say a three-prong plug. We're going through the ground wire, and now here you can see we have our low impedance path to ground. And it's going through there and returning, going back to the current source, and in this case we are talking about a pass. So this is essentially, it's very simple what's going on with a ground bond test. We could run into a situation where it can't handle the fault current, or that bonding point wasn't properly connected, and then we're going to get a fail. And usually with a ground bond tester, that's in the form of a resistance high limit. It'll say you want greater than 200 milliohms, or you want greater than an ohm, or whatever the case might be. If the resistance is too high, it's considered a failure. Because if we want to facilitate that extra current to flow to ground, we have to make that current path very attractive. So lower resistance, the better. As everyone knows who's ever dealt with electricity, current's lazy. So it's going to take the path of least resistance. So the lower the resistance we can make that ground path, the better, because it will facilitate current flow to that ground path. So just a quick recap of talking about the bonding versus the continuity. The continuity test verifies the existence of the ground test, or the ground connection. The bonds test verifies the integrity of the ground connection. Generally, when you're dealing with a continuity test, you're usually dealing with a reading in the ohms range, whereas a ground bond test, you're usually talking about the milliohm range. And I understand I'm speaking in generalities here. Obviously, there are going to be standards and tests that you run where that might not apply, but for the purposes of this webinar and many of the other standards out there, this does apply. So for a ground continuity test, it's a quick setup, easy to perform. So it's very simple, and it's good for a production line atmosphere, especially because it is so quick. You don't need time for that high current value to settle and make sure that your bonding or your bonding path can actually handle that current. But the ground bond test, even though it usually can take a bit longer, it does provide more valuable safety information about the DUT for the reasons I explained previously. And then the continuity test, it's usually used as an extra feature during a Hipot test. So a lot of times people will run a continuity and Hipot test in tandem. And the bonding test, I feel, can be combined with a Hipot test for a more complete safety testing system. Even when a bonding test isn't called for in the production line, I generally recommend it. Now, I think continuity is only required per UL1703 for a production line environment, and that's fine because through your sampling you've probably gone through your bonding tests, but it can't hurt. That's all I'm saying is if you're doing a bonding test on the production line, it really can't hurt to make sure that nothing happened during the production process, especially if you have a concern that the integrity of that grounding circuit could have been compromised. Now, this is a perfect example of where a bonding test really can have its advantages over a continuity test. Take the example of a 64-strand wire for a bonding conductor. And let's say all of those strands were cut except one. An extreme example, I understand, but this has happened. I've seen this happen. So A continuity test, as you see on the top there, it's just looking for a path. It'll find it, and it'll give you a pass. And then if this is the only test that you did going out the door, and it ships that way, there could be an issue. Now, I think this would be an extremely rare, non-existent case if you're actually doing it in a production line. Like I said, your design testing has probably proven this out. But a bonding test is essentially that one strand is not going to be able to handle that amount of current. It's going to fry up the wire. The test will fail as it should. So that's just a quick example here. Now, let's jump into the Hipot test because I've already mentioned it several times when talking about the continuity test, and I don't want to mention it anymore before we get a chance to discuss it. The dielectric withstand test, which is commonly called a high potential test or Hipot for short. I will refer to it as a Hipot test throughout the remainder of this webinar. It's basically used to stress insulation on a product far beyond what it's going to encounter during normal use. The idea behind this is if it can handle that level of stress for a specific period of time, it should be able to operate throughout its life cycle without a problem. So basically, you're just wailing on the insulation with a lot of force, in this case voltage, to make sure it can stand up to it. And if it can handle it, you're probably in pretty good shape. The high voltage is generally applied from your mains input lines, and then your return point is generally the chassis. And you're going to be basically monitoring the amount of leakage current that's flowing through your insulation. So if you think about it, when you run a Hipot test, you're pretty much kind of creating a capacitor, because on one side of the circuit, on your high voltage side, you have your mains conductors, usually which is line and neutral. You're shorting those together. And on the other side, you have your ground conductor, and sandwiched in between is your insulation of your product, and you're looking at how much leakage current is flowing through that insulation. This is a valuable number because it's telling you how much somebody could be exposed to in the similar type of condition where you get a power surge or something along those lines. So a couple terms I want to define here because they sound the same, but they are quite different, and you'll see some of these terms used in the standards themselves. When you're talking about a dielectric withstand test, there's breakdown and there's what we call disruptive discharge. Breakdown is what we're looking for with a Hipot test. This is what we want to know. Did our insulation break down? It's basically a complete failure of your insulator or your dielectric material. Your leakage current might be going up and up and up and up and up, and then all of a sudden the voltage bridges that gap. At that point, your insulator ceases to be an insulator. It becomes a conductor, and your current increases exponentially. And like it says there, it's an abrupt increase in the flow of the electrical current through the insulation. That's exactly what we're looking for a Hipot test. If your insulation can't stand up to the voltage, it's going to snap over, and with most modern Hipot testers, it's literally going to say breakdown on the screen because it recognizes that condition. There's also something called a disruptive discharge. Now, this could be a breakdown, but in most cases, it's a little different. It's a discharge that bridges the insulation, reducing the voltage across it practically to zero. Now, that sounds just like what I said for breakdown, but might not necessarily be the case. Let's talk about running a couple repeated Hipot tests, right? Let's say I run a Hipot test on a solar panel, and it says breakdown, and I get a breakdown at, oh, let's just say 1,000 volts. I run the test again, and again I get a breakdown. This time it's at 200 volts, and let's just say for the heck of it, I run the test a third time, and now my breakdown's happening instantaneously. That's a pretty good indication that you actually have a true breakdown because your insulation has been compromised, it's now a conductor, and it's breaking down immediately. There's not even a voltage buildup this time, it's just a short circuit path. A disruptive discharge, however, you could run into this case where you run a Hipot test, and again, you get a breakdown, right, at 1,000 volts. You run your Hipot test again, and it magically passes. And I've seen this time and time again. And you're scratching your head, and you're wondering, how did this Hipot test pass when it broke down the first time? Well, a lot of production floors can be very dirty environments. Or even in the manufacturing process, you can get small particulates that build up in the insulation. What can happen is that when you run your Hipot test, there's enough stress there for the voltage to bridge across these particulates and cause a discharge. When you run the test again, what happened when you ran the first Hipot test is you essentially burned those particulates away. They're not there anymore, and now you have a solid layer of insulation, and now you're fine. If you were to run that test a second time and get a pass, that would, by most agency standards, be considered a pass, because that first one wasn't a true breakdown. Your insulation's actually fine. You just had some particulates or maybe a humidity or some kind of water droplets built up in there, and when they got fried away, you were okay. So these are two important things to understand. So this is the most common type of safety test, and it's used as a design test and a production test, and it's generally a 100% production line test. This is true of the UL1703 standard that calls out for this as a factory test. The IEC standards don't specifically say this is a factory test, but I would sure think and hope that this is the test that's being done at the end of the line production, as well as in the prototype phase. Because it can be used to detect workmanship defects. Who's to say that while your solar panel was being constructed that maybe some insulation wasn't clipped by a tool? Whether that's automated or not, these things can happen. Or it gets frayed by rubbing up against the frame or the chassis of the solar panel. I've seen these things happen on production floors, so it's generally a good idea to run this just to make sure right before you ship the thing that nothing happens. Now the insulation resistance test is actually extremely similar to the Hipot test in most senses. But in this case, you're providing a quantifiable value for your insulation. Now remember, for the Hipot test, basically we're measuring leakage current. Well, for the insulation resistance test, we're doing the same thing. We're applying a high voltage and we're measuring leakage current, except the unit will convert, using Ohm's law, will convert that leakage value into a resistance value. And that tells you exactly how much resistance that your insulation is providing. So it's similar to a DC Hipot test. It stresses the same insulation on the product as the Hipot test. And you're basically doing this DC flash test at usually 500 or 1,000 volts. For the solar panel standards, it's a little bit more because of how they define that, and we'll get into that in a little bit. So you're displaying a resistance measurement by dividing the voltage applied over the leakage current produced, and you're getting an actual value in mega ohms or sometimes even giga ohms, or some IR or Megger testers go up even higher than giga ohms. But that's not really necessary for the solar panel standard, as we'll get into. The range is in the mega ohm. If you get into the hundreds of mega ohms range, it's usually sufficient. So if you have an IR tester that goes into the hundreds of mega ohms or giga ohm, that's generally sufficient for an IR test per these standards. So this is essentially what's happening for the Hipot insulation resistance test. As I mentioned, you can see on the left-hand side, we have our current carrying conductors, and for a solar cell, it's usually a plus and minus. We're dealing with, usually these are DC. There are some AC out there, but I use the DC example because it's much more common. We have our plus and minus terminals on our solar cell shorted to high voltage. And then as you can see, we have our black return wire on the chassis or the frame. Not all solar panels, I understand, have a chassis or a frame. If they don't, usually what the standard says is that you wrap a portion of it in foil, and then you use your return point as a conductive point as that foil, because you're simulating conductive contact. That's what you want to do. In some cases, you're even using a saline bath as your conductive return point, which I think is much more accurate because you're covering as much of the solar panel as possible. But we'll get into that in a bit. So what's happening here? If we represent this diagram as a circuit, essentially what we have here is, you can see we have a standard, we have a fuse. You can still see high voltage tied to plus and minus. We have our little fuse in there. And you'll see we have two capacitors. I've simulated the insulation as these two capacitors because they're going between your mains circuit and your chassis point. So you have these capacitive values, and sometimes you can even have capacitive coupling to ground when running these tests. That's essentially what you want to measure. You want to measure the leakage current flowing through those capacitors. So in this case, we can see we have a pass. We have a little bit of leakage current flowing through that cap. Our unit registers that leakage current and gives us the all clear. But we can also run into a case as we get a breach in insulation, we get a direct short across that capacitor, and we get a breakdown. Just what we discussed in the previous slides. And this is just shown. It's a very simple example, but it also is actually very closely representative of what's happening with a Hipot test and an IR test. Now let's get into the standards a little bit, because there's main ones I want to cover here. The main standards that I usually look at when I'm dealing with solar panel stuff are UL1703, IEC or EN 61730, 61215, and 61646. You might notice that I didn't list 61730 on here. This table, there's actually a very similar table in 61730 that outlines the same information. I've basically broken that down and focused on the tests that I want to talk about here. And of course, this is in the interest of time. There are many more tests. Unfortunately, we can't get into them all right here, but hopefully we can give you a better understanding, if you are running these Hipot, IR, and leakage current tests, of how to do them and why you're doing them. So they refer to these as MSTs for your tests. And you have your ground continuity test, and then obviously that's not required unless you have a metal frame. If you don't have a metal frame, well, what's the point of running a continuity test to what? You're not going anywhere. It's the same thing as a product that has two ground prongs, or two prongs instead of three prongs. If you have a three-prong product, that third prong is your ground pin. Well, if you only have a two-prong product, that's a Class 2 product. You have a layer of double insulation. You can't run a continuity test because there is no chassis point. All you have is a dual layer of insulation instead. It's a similar concept with the solar panel. Not every solar panel has a chassis or a frame. So not every solar panel is going to have a ground bond or continuity test run on it. So the ground continuity test is specifically referenced in UL1703. They don't talk about it in 61215 or 61646. They do talk about it in 61730 and 1703, and they basically say the same thing. They say, hey, if you don't have a chassis, don't worry about this test. I've obviously greatly simplified what they're saying, but that's the gist of it. Then you have your dielectric withstand test, which is in all of these standards, but as we'll talk about in a little bit, 61215, 646 don't call it a dielectric withstand test. They actually just call it the IR test. But as we saw in the previous slides, it's the same concept. You're kind of measuring the same thing. And then we have what's called the wet leakage current test, and this one is a little bit different, and I'll discuss this on its own. Now, I made a note there that the pass-fail conditions differ on 61215 and 61646. They do. It says that in the 61730 standard. They do differ, but they're also pretty darn close, so we're going to talk about that as well. So let's look at the ground bond specs first, and I wanted to lay this out in kind of a hierarchy so that we can separate these two standards, but look at them on the same token. So for the PV ground bond specifications, and keep in mind, again, we're only dealing with something that actually has a chassis. If it doesn't have a chassis, there's really not much point to do this. So this is, I believe, section 25 in the UL1703 standard. And I want to say this is section 10.4 or MST13 in the 61730 standard. The 61215 and 646 do not talk about this one, but again, since 61730 is kind of the granddaddy standard, and then 61215 and 646 fall under that one as more specific examples of photovoltaic modules, the same concept can be applied. So for 61730, basically what they're saying is you're applying a current of 2.5 times the maximum overcurrent protection of the module, and you're running this test for 2 minutes. So they're really having you load down this ground circuit path, and the test is required only if the module has exposed conductive parts. This is what I was saying before. If there are no conductive ports, there's really no point. Your maximum limit is 100 milliohms, or 0.1 ohms. This is actually a very common high limit across multiple standards. And you can see the UL1703 has adopted that same idea. The current's a little different. It's equal to twice the fuse ampere rating to be passed between the ground terminal and any conductive part. So even though the current value is slightly different, the limit is the same. It's 0.1 ohms. So this is pretty straightforward. As I showed you guys in the circuit diagram, you're just applying current on a conductor and seeing if it fails the test. That's really it. There are differences too, and we're talking, I've already mentioned production and type testing in a couple different guises when we were going through this. The ground bond tests for 1703 and 61730 are what we call type tests. Those are your laboratory, your sample tests, where you're grabbing a couple samples and you're running these tests. It's not required for a 100% production line. Like I said before, I think it's a good idea, but most people don't do it. There's cost and time concerns involved with that, so I get it. 1703 actually does specify, however, production line ground continuity testing. It must only demonstrate electrical continuity. So in the UL spec, it's section 45 in 1703, and section 45 specifically relates to a production line test. It says, each module or panel provided with a connection for grounding accessible conductive parts shall be subjected to a routine production test to demonstrate electrical continuity. So they don't get specific here. They just say any appropriate indicating device, such as an ohm meter or a low voltage battery and buzzer combination, may be employed for this test. So they're basically just saying, hey, just make sure there's a path. You don't need to load it down. If the path is there, you're good to go. That is production line. So 61730 doesn't talk about production line tests, but I would have to imagine that this is also being done for those manufacturers in Europe that are testing to 61730. They leave it to the manufacturer's discretion when they don't specify it. Most of the customers that we deal with, they're doing this anyways as a simple continuity test, and it makes sense. We even have some customers that do the bonding test for just a quick 5 seconds on the way out as a production line test as well, which I think is a great idea, but it's obviously not required. Now, we're talking about the Hipot test. You'll see there's a little bit of a difference here. Now, as I already mentioned, it's only the UL standard that talks about production line testing. They get into it specifically at the end of the standard, starting on page 63 with the production line test, which starts off with section 43. And that's where section 43 talks about production line Hipot testing. Again, for 61730, 61215, and 61646, they don't specifically mention factory tests. They leave it to the discretion of the manufacturer. So what they do here, though, you'll see is in the Hipot test for the UL, the type testing one for the UL standard, and all the other standards actually, they usually have you run it for 60 seconds. And the test voltage is anywhere from 500 volts to 2 times system voltage plus 1,000. Some of the standards actually a little bit higher. What they allow you to do, because they understand that in a production environment, 60 seconds can be a long time, especially if you have hundreds to thousands of modules going out in a given day. You don't have a minute to do each one on. So they allow you to reduce the test time to 1 second, but you have to increase the 60-second test voltage by an extra 20%. So let's just say your test voltage is 1,000 volts for your type testing. So for your 1-minute test, your test is 1,000 volts. Well, it's going to be 1,200 volts if you reduce that test time to 1 second. So that's something to keep in mind, and they do outline this specifically in the UL standard. If you're dealing with an IEC or EN standard, this is a pretty good thing to adopt if you're going to reduce your test time. So the dielectric withstand test, the 61646 and 61215 describe the Hipot test as part of the insulation test. They don't call it the dielectric or Hipot test. They call it the insulation resistance test. And as I mentioned before, you can kind of mingle the terms together. There's a gray area there. They're essentially doing the same thing. We're checking for a safety hazard, and as long as there isn't a hazard, we don't really care what they call it. So 61730 does specifically list the dielectric withstand test, and it also has some extra stipulations depending on you're talking about Class A or Class B, which is something that I found kind of interesting. So in section 10.6 of 61730, which is MST 16 test, they say this test is identical to the test 10.3 from IEC 61215 and IE 61646 with test levels depending upon the application class and maximum system voltage. Where it differs is in this standard, the 61730, they say the maximum test voltage shall be equal to 2,000 volts plus 4 times maximum system voltage for application class A, and 1,000 plus 2 times maximum system voltage for class B. So you can actually get a bit of a higher test voltage here when you're dealing with it. And I believe if you have a 1,000-volt module, your test voltage goes up to 6,000 volts. According, if it's a class A one and you're 1,000 volts, you have to test it at 6,000 volts DC. And then in the 61730 standard, They say the pass criteria, they don't give any. They just say see IEC 61215 and 646. So they kind of fall back on 61215 and 646 for the pass criteria. The pass criteria there is pretty straightforward. And I'll get into that in a second. So UL1703 refers to it as a dielectric withstand test. They do call it this. And this one's a little bit different, though, because unlike the IEC standards, the UL standard actually gives you a high limit for your leakage current. And that high limit is 50 microamps. And it must be tested in both polarities, meaning if I test it with my high voltage shorted to my mains conductors and my return on my chassis point or my foil or my saline bath or whatever the case is, then you run that test, then you go run another test where you would apply high voltage to the chassis or the saline and return on the mains conductors. So you're just flipping the polarity. This makes sense because obviously you want to make sure that the insulation can handle it in both polarities. Now, the equipment used for the Hipot test, the UL standard stipulates that you have to have a 500 VA capacity. However, this 500 VA capacity rule for the Hipot transformer doesn't apply if your voltage is measured on the output. Where does that come from? Basically, what they're saying here is they're making sure you have a regulated Hipot tester. Because if your Hipot tester does not have a regulated output, what can happen if you heavily load it is your voltage can drop with a heavy capacitive load. So if your voltage drops with a heavy capacitive load, you're technically not testing at full voltage, and you didn't run the test properly. However, if it's regulated on the output and has a feedback loop, ensuring that the output is constant, you don't have to worry about that, which means you don't have to have a very high capacity unit to handle such heavy loads. So that's something to keep in mind. We've had customers call us and say, hey, I need a 500 VA unit, do you guys have one? And we get into the discussion and we find out they're testing solar panels and we say, Mr. Customer, if you look at this exception to the UL standard, you can see you actually don't need one. All of our Hipot testers have a regulated output. And it's not just our Hipot testers. I think most of them on the market right now have a pretty well-regulated output. So this exception for the UL standard can be applied to most Hipot testers out there. The IEC standards don't specify such a regulation with the 500 VA, so it really doesn't apply to those. So let's look at pass-fail criteria, because this is something I was just talking about. For the IEC standards, they basically say no dielectric breakdown or surface tracking shall occur. Surface tracking meaning if you apply a Hipot test to a solar panel and you see a little corona or you see static discharges across the surface of your solar panel, that's probably not good. You could have some delamination, you could have some bubbles in there that you really can't see too well, and the Hipot test is going to let you know if you have those things. You're going to be able to either see it, hear it, or the unit's going to give you a breakdown failure. But it doesn't specify specific leakage current high limits. What it does specify are insulation resistance limits, and that I will get into in a few moments here. The UL standard states that there also should be no breakdowns, no signs of arcing or flashover. Pretty much the same as the IEC standards. If you have surface tracking, that would be considered arcing, flashover, things of this nature, but they further specify a current high limit of 50 microamps, which is fairly restrictive. But if you compare that to the insulation resistance limits of the other standards, you'll see that they're actually pretty close. So, as I mentioned before, here's a setup for a Hipot test using one of our 7650 units. In this case, I'm using, as you can see here, I'm using what we call a multiplexer. The thing I like about these channels on this multiplexer is they can be, there's internal relays. So any of these channels can be set to a high point or a low point. That's nice if you have to do a reverse polarity test, because what I can do for test number 1 in an automated fashion is I can have relay 1 here set to high, run my Hipot test, relay 2 here set to low so that I have a return path. Then, in an automated fashion, I can internally in the unit on the second step have it automatically flow into a second test where high voltage is applied here and the return point is applied here, thus effectively doing both polarities in a single shot. So really no different than the last diagram we looked at. In this case, I just used a multiplexer, so if I'm on a production floor and I need to run my test in both polarities, which you do, I can do this in an automated sense so that the operator doesn't have to go changing settings or clipping leads in different spots between each of these tests. It kind of takes out the human element too, in the event that somebody might screw it up and not clip on a proper return point or might not get a good connection. This kind of takes that out of the equation. So, I've been talking about these resistance limits because, as I mentioned, the IEC standard specifies values for pass-fail criteria per resistance limits, not leakage current limits. Well, it does boil down to kind of the same thing. It's important to know those limits. So what are we talking about here? Well, let's look at the IEC standards. Obviously, it says no breakdown shall occur. All the standards say that. Obviously, you don't want your insulation to break down, whether you're doing an IR test or a Hipot test. But you'll see that I have a lot of words there, but it actually, the 61215 and the 61646, it says the exact same thing. And actually in the UL1703 wet leakage test, it's the same values that you see here. So these apply across the board. It just depends on what test you're talking about. Because these values only apply to the UL1703 if you're doing the wet leakage current test, whereas in the 61215 and 61646, as well as 61730, so all the IEC standards, these numbers apply to both the dielectric withstand/IR and the wet leakage current test. So they're basically numbers that are used all over the place. So it depends on module area. If the area of your module is less than or equal to 0.1 meters squared, so a relatively small solar cell, your insulation resistance value has to be greater than or equal to 400 mega ohms. So basically they're saying small panel, you should have a pretty decent insulation resistance value because you don't have much of a surface to work with here. So even if you completely wetted that entire surface, you should have a high insulation resistance value. However, if your module area is greater than 0.1 meters squared, the measured IR value times the area of the module shall not be less than 40 mega ohms times your meters squared. So they understand in this case that the bigger module, if you're wetting the whole thing or putting the whole thing in a saline bath, you have a lot more surface area there. So they give you a little bit more tolerance on the values. But you're still in the 40 mega ohm range or greater. So you could be, or it could technically be less. Let's say you have a 0.2 meters squared, then you're talking 20 mega ohm. But you're still talking the mega ohm range. And if you're talking the mega ohm range, with a voltage of 1,000 volts or more, you're still talking sub-amp here. You're talking milliamp to microamp range of leakage currents here. So it's important to remember that we're still dealing with very small current values when we're talking about these high resistance values. You could do a simple Ohm's law calculation to figure it out. You really are going very small current values, and this makes sense. The smaller the current, the better. Somebody to walk up and touch this thing, we want them to either barely perceive this current. We don't want it at dangerous levels. So this is where some of those limits come into play. Now the wet insulation resistance test is a bit different, but like you saw in the previous slide, we're dealing with the same values as far as pass-fail criteria. So just keep those in mind. The difference here is it's designed to analyze a module's insulation after exposure to moisture in your operating environment. So as everyone knows, a lot of these they're going outside. They're going on people's roofs, they're going in big solar parks or big solar farms, or they're going on vehicles, whatever the case might be, they're going to be exposed to moisture, fog, rain, snow, dew, whatever the case is, the insulation has to be able to stand up to these conditions. Now, the wet insulation resistance test is type testing only. You don't have to do this on the production line, which makes sense. This might be a pain to do on the production line, although I have seen people do it on their production floor. For type testing, it's performed at several stages of the design qualification, and refer back to your standards for that one. We don't have time to delve into that, but it's actually run several times, and there are criteria for the conductive medium used. It's a solution. It's not just straight up water. You can't just take tap water and then dip the thing in and run the test. Despite what people think, tap water is not as great of a conductor as you might think. But the advantage here is this wet IR test allows for complete conductive coverage of the PV module, so you're getting a very good value here. This is a true worst case value, and when you're doing tests like this, that's what you want. You want worst case to make sure this isn't going to be a safety hazard. So it has various specifications on the properties of the solution. For example, if we look at UL1703 or IEC 61730, you have a 35 ohm meter maximum surface resistance with a 22 degrees C plus or minus 3 degrees C temperature to the water. How could you get this ionized solution or saline solution, so to speak? You need to break up the surface tension a little bit. Tap water actually has a fairly high surface tension. Like I said, it's not as good of a conductor as you might think. However, if your solution's saline or you break up the surface tension, you can get within these parameters. So an example is, let's just say, deionized water with a Liquinox detergent solution, because detergent is a surfactant. It will break up surface tension. That's just an example of how you could create the solution to run this test. So a note here on the wet insulation resistance test: components not designed to be submerged, like your junction box. You don't have to submerge them completely in the solution, but they do have to be sprayed. They still have to pass the spray test, and they have to be wetted because they are going to be outside and they are going to get wet. And as we already mentioned before, the same pass-fail numbers apply here as far as those mega ohm values we discussed in the previous slides. So the tested method is the same as it was for the dielectric withstand and the Hipot test. You short both of the mains conductors together and return on either a dead metal chassis or foil or saline bath or whatever the case might be. You use this conductive medium to contact the panel, and then you get a reading. Now, one thing I wanted to note here, because we did talk about testing in reverse polarity, and this is something that you have to do. What most people do, and even when I use my multiplexer, this is essentially what I was doing, just in an automated fashion, and instead of me manually doing it, I was using relays to do the job. You're just swapping the HV and the return leads. The thing you want to be really careful of here is testing in reverse polarity in this way will cause that conductive medium, whether it's foil or a saline solution or whatever, to become energized. So you should really be careful. Take your necessary safety precautions. You don't want to be rubbing up against a large metal table or conductive foil if it's got high voltage on it. It's going to be a bad day for you. So you're going to have a very large energized surface, so just be very careful when you're running this test. Now, the light from the testing environment can energize your cells. So when you're running these tests, try to cover up your panel, because energized cells can cause an increase in the leakage readings, which can cause false failures and can also introduce potential onto the return line, possibly damaging your Hipot tester. I don't think this is common, and I think cells are built in such a way where it shouldn't be enough to nearly affect anything. It probably wouldn't even be perceptible to you unless you really bathe this thing in light. But it's just something to be aware of when you're running this test, is if it is energized, it's just like a battery being energized, and then you're applying a Hipot test to it. You want to be careful. So let's look at a complete setup. In this case, I'm using our Omnia 8204. That's a new tester that we've come out with, and this would be your full-blown setup. I can run my ground bond, my Hipot, and my IR all with this connection point. So for my ground bond, I have it connected to a ground bond channel here, and I have a common return point here. So I'm injecting high current right here, and I'm letting, once again, these multiplexers, these relays, handle everything automatically. And then I have my return point on my chassis or my frame here, and which will provide a return path for my ground bond test. So it would go through, close those relays, run that test, then it would open those relays and automatically flow right into my Hipot and IR tests. So then I can run this by shorting these two conductors and, again, returning on my chassis right here to complete the cycle. Then finally, let's say I was testing reverse polarity. Mouse is jumping around here a little bit. If I was testing reverse polarity, then I can automatically open those relays again and flow right into the test where I apply high potential here to reverse the polarity and return on my mains conductors. And that pretty much completes your test cycle. Since the IR test is the same thing, you would actually set the exact same relays for that test. Now, I know we covered a lot of information here, so if you do want copies of the slides to review, let Jim know, and he can get a copy out of the presentation to you. This webinar will also be available in a few days on our website, so check our archive at www.asresearch.com/events/webinar archive. If you do have questions regarding this material that we weren't able to get to today, give us a shout, info@asresearch.com. We deal with customer inquiries all the time. We have a dedicated applications department, and we're able to handle things like this. So once again, we appreciate everybody who attended the webinar. This is our last webinar for the year, but join us in 2014 for our next series. Thanks again, and I will leave it open for a few minutes for any questions. I did get a question that popped up here. It says, can you confirm that the resistance of the big panel should be 40 mega ohms times meter squared or divided by meter squared? That's a good question, because the way that it's worded in these standards, it's a little bit tricky, and that's the way I did say it. What it says exactly is, for modules with an area larger than 0.1 meters squared, the measured insulation resistance times the area of the module shall not be less than 40 mega ohms squared times, or 40 mega ohms times meters squared. So if you were actually doing the calculation for the IR value, you would technically divide it to get your IR value. But the way it's stated in there, it almost looks like they're saying you would multiply it. That is not the case. Otherwise, you just get a huge number for the big panels, and you'd want that to be lower. So the way that they state it's a little bit tricky, but if you write it out as a mathematical formula and solve for IR, you will see it's not exactly the way that they said it there. But that was a good question. And we did get another one. What are the main ways to protect users from shock hazards during Hipot testing? And that's a really good question. There are a variety of ways that you can protect users from shock hazards. I can't get into them all right now because that's a pretty loaded question. You're dealing with OSHA regulations. You could also be dealing with various regulations if you're in Europe, EN 50191 regulations. There's safety approach boundaries. Wearing personal protective equipment is another way to protect users. Using an enclosure. So what I mean by that is completely enclosing your product in an enclosure such that the operator cannot touch it while the test is running. All of our Hipot testers have an interlock. If that interlock is opened, the test automatically stops. So what I do in the lab a lot of times is I will actually run the interlock through a DUT enclosure door. So I'll put my product in the enclosure, shut the door. Once the door is shut, that shorts the interlock and it allows the test to run. Should I open that door for any reason during the test, that interlock, because the door is open, the interlock also opens because it's wired directly to my unit's interlock, and the unit shuts off immediately and stops the test so that I cannot contact it while it's running. Wearing high voltage gloves is another way to protect the user. Having the user stand on a high voltage insulation mat to ensure that they are not at a ground potential is yet another way to protect the user. There are a whole slew of things out there that you can do to protect your user. I've just named a few. If you want more information on protecting your user while running a Hipot test, I would recommend you visit our website, asresearch.com. You're going to find a tab for support, and there's something called the Operator's Guide. And the Operator's Guide talks about things you can do to protect your user. Another good reference is the OSHA website. OSHA website has free information on it talking about the knowledge that your operators, if your operator is using a Hipot tester, they should be trained to use that Hipot tester. They have to be a trained operator. They are working with a dangerous piece of equipment. It's like working with any other dangerous piece of equipment. You should know how to use it before you jump in. So reading product literature, manuals, knowing what to do, knowing the hazards are key components as well. But if you go to our website, go to support, or look at the documents, look at our documents, and you'll see the Operator's Guide. That's also got some additional references in there. So I'd recommend you do that, but obviously if you have more specific questions, please feel free to contact us. Well, it looks like that's all the questions for now, so I'm going to cut the webinar here. If anybody happens to think of a question or wants to get more in depth, give us a shout, and we can certainly do so. But once again, thank you for attending.